Okay, now we're going to learn how to use the HR diagram of your Earth Science Reference Table. A number of years ago, two scientists named Hertzsprung and Russell decided to do an interesting graph of all the stars in our neighborhood. They plotted on a graph the star's temperature versus the luminosity. Now, luminosity, as you know, is the absolute magnitude of the star, the true magnitude, but on a slightly different scale compared to the sun. So instead of being magnitude of -1 or +2, like other magnitudes, luminosity is just simply a relative scale compared to the sun. 10 times brighter than the sun, 20 times brighter than the sun, and so on. Very easy for comparison. Now, on the x-axis, you have temperature. Now, in temperature, you notice something very odd about this scale. It's actually increasing toward the left. That's a bit foreign to you. You're used to having scales on your x-axis get larger as you go to the right. Well, it's doing the opposite here. So remember, your lowest temperatures are on the right, your highest temperatures are on the left. And a little point of review. The cooler a star is, the longer the wavelengths that it emits. The hotter the star is, the shorter the wavelengths that it emits. And that's why the cooler stars tend to be red, and the hotter stars tend to be more on the white or blue side, because these are the shorter wavelengths. Blue is a shorter wavelength than red. Now, the next thing I have to remind you is something that some students have had difficulty with in the past. This is not a map of the night sky. It's not a map of our solar system or our galaxy. This does not show relative positions in space. This shows values of luminosity and temperature. So there's no movement going on here. There's simply changes in temperature, changes in luminosity. So please do not mix this up with any kind of a map, because it certainly is not. Now, you'd think that when you graph a whole bunch of random stars, you get random distribution of points on your graph. But Hertzsprung and Russell did not get that. You'll notice the stars appear in distinct bands on the graph. We have a very distinct band right along here, which most of the stars appear in. And then we have 2 to 3 other smaller groups. We have a group down here, and we have a group on the upper right, and one a little higher. We don't have much going on in certain areas. You'll see my cursor, there's no stars really here, nothing really here, nothing in this area. Very interesting. Now also, if you notice the number of dots, well, that poses an interesting question. This band right here, these are the stars that are on the main sequence of their existence. All right? They're fusing hydrogen to make helium. The stars in the upper right group are red giant and supergiant stars in the later stages of their existence. And then in the lower left, we have these small hot group right here, white dwarfs, which are in almost the last stages of the star's existence. Now, why do we have so many more stars in the main sequence? What can we infer from that? Well, what we can infer from that is that a star is going to be spending most of its existence in the main sequence, and then it'll spend less time in the giant and white dwarf stages. And that explains why when you examine the universe around us, you see more main sequence stars than you do giant stars. The reason simply being, there'll be more of them because stars spend more time as a main sequence star than they do as a giant star. Now, you actually might have noticed something like this last year in life science when you were examining a root tip from mitosis. If you recall, most of the cells you found down there in the root tip were in interphase. They were not in prophase or anaphase. They were in interphase because cells spend 90% of their time in interphase. So a similar analogy can be made here. Stars spend more time as main sequence stars, and therefore you'll find more stars in the main sequence when you examine the night sky. Now let's take a closer look at how to basically use this graph. Let's take a look, for example, at the sun. And let's take a look at the sun's luminosity. Now, the sun's luminosity is a 1. It is equal to itself. Everything here is compared to the sun. The sun is as bright as the sun, and therefore has a luminosity of 1. Now, let's take a look at Sirius. Sirius. Now, what would Sirius's luminosity be? Now, let's follow this over. It's somewhere between 10 and 100. But notice, the scale is what they call a logarithmic scale. We go from 10 to 100 to 1,000 to 10,000. So we're sort of increasing exponentially as we go up the axis. So we're probably not going to be going 10, 20, 30, 40, 50, 60 in even numbers here, in even intervals. So when you interpolate, it's going to be a little strange. This right here is probably going to be something like 20 or 25 times greater than the sun. Now let's go a little higher. Let's take a look at, let's say, Aldebaran, the brightest star in the constellation Taurus. Now, this is halfway between 100 and 1,000. So I suppose it could be 300, 400, 500 times more luminous or brighter than our sun. So, we're not going to be very exact on here because of the nature of that axis. We're going to be dealing with some pretty approximate or ballpark figures. How about we take a look at some real impressive stars? Let's go all the way up here to Rigel, since we've talked about that one in class. How much brighter than the sun is Rigel? Well, let's sort of follow our line across. Now, Rigel is over 100,000 times brighter than our sun is. So it's looking like, if we interpolate crudely, maybe 150,000 times brighter than our sun. But we could be off by quite a bit with this axis. Either way, imagine replacing the sun in our sky with something that's 150,000 times brighter. It's pretty tough to imagine. Now, that's how we use our scale, for at least the y-axis scale for luminosity. Now, let's take a look at the temperature scale. Temperature here is measured in degrees Kelvin, which scientists refer to often just as kelvins. Now, let's do some rough approximation. We have 2,000, 3,000, 4,000. They're all, these are 1,000 apart. Now, a similar distance here brings us 2,000 apart. Another 2,000 is gained. Now 2,000 is gained very short. Now an entire 10,000 is gained in that distance. And then another 10,000 is gained in an even shorter distance. So this is a bit of a bizarre scale. So you're going to have to just do your best to interpolate between the numbers, and chances are you're going to get something that's going to be correct. So how about we take a look at our sun? What is the temperature of our sun in degrees Kelvin? There's 4,000. There's 6,000. That's obviously going to be 5,000. So I would say probably something like 5,700 degrees Kelvin. That looks about right. 5,700 kelvins, as they would say. Now, if this were Celsius, it would only be 273 degrees off. So it would still be, between 5,500 and 6,000 kelvins. So if you're ever asked to provide the temperature in degrees Celsius, you can still use this scale and get a pretty decent answer. Because when you're dealing with 6, 7, 8,000 degrees, a difference of 273 degrees is not all that significant. So even though it's Kelvin, we can still get decent answers on a Celsius question. Now let's take a look. What is the temperature of Aldebaran? Since we mentioned that one before, well, maybe we didn't. That's the brightest star in the constellation Taurus. Now we bring it down here, and it looks to me like the temperature of Aldebaran would be about 3,900 Kelvin. Okay, let's try a really hot star. Let's go all the way over to Spica, which is in the constellation Virgo, and it is an incredibly impressive star. Looks like it's halfway between 20,000 and 30,000, so I don't think we'd ever have a problem saying 25,000 degrees Kelvin or 24,000 degrees Kelvin. So now we're getting an idea how to use these basic functions of the HR diagram. Now, let's take a look at something else. Let's take a look at how a star's existence changes over the course of its development. Now, first, as we know, as we learned, a star forms from a protostar that has begun doing nuclear fusion in its core. Once the fusion of hydrogen into helium begins, we officially have ourselves a star, and that's a main sequence star. So, a star is going to officially begin being a star someplace along the main sequence. These would be your smaller main sequence stars, and they're not fusing very hot, only 3,000 degrees or so on the surface. So they're not particularly hot stars. They're smaller. They don't have quite the exciting amount of fusion that's going on in these giant blue main sequence stars up here like Spica, which are much more impressive. These stars here, because they're larger, they have a more intense, greater quantity of fusion going on inside of them. They're going to have a hotter temperature, and they're going to tend to have a more bluish color. So these are spectacular stars. Now, the star is going to be a main sequence star like our sun, and once the hydrogen runs out, it begins to fuse helium, and it becomes a red giant. It's going to then continue its existence as a red giant star until it has used up all the helium, which has been fused into things like silicon and carbon and oxygen and iron, the larger elements. Once that helium is gone, now the giant star blows off its outer layers, which then become a planetary nebula, and what remains behind is a smoldering, hot little white dwarf, which was the core of that giant star. So you'll see the path goes from here to here. Now remember, once again, this is not motion. This is not a map. This is just changes in its development. Now, let's ask ourselves this question. When a star, like the sun, goes from a main sequence star to a red giant, what happened to its temperature? Well, the temperature got cooler. The temperature went from here to here. The temperature got cooler. We moved to the right. Now, what happened to the star's luminosity when it became a red giant? Well, luminosity went from around here to around here. So the star became much more luminous. But why? Did it become luminous because it got hotter? Absolutely not. It got cooler. So how in the world can a star get cooler and become more luminous? There's only one explanation for this. It must have become much, much larger. And it did. Now, after the planetary nebula is discarded from the red giant star and it becomes a white dwarf, what change happens to the luminosity? Well, obviously it becomes much less luminous. It goes from a position up here on the y-axis to a position down here. So it became much less luminous. But what happened to its temperature? It went from 4,000 or so to something around 14,000, 15,000. So how can a star get hotter and yet become less luminous? I'll give you a second to think about that. Well, the answer is the star became much, much, much smaller when it became a white dwarf. They're hot, but they're very small. So now we have the basic developmental changes that we can infer on the HR diagram. Now, these bigger main sequence stars, which tend to be bluer, Well, it's believed that when they become giants, they become supergiants. Okay? Um, so now let's take a look at a couple other things that we can do with an HR diagram. Now, the first interesting thing that we can do, probably the most challenging thing we can do with an HR diagram is infer size. Now, let's think about this. There's two things that give a star its brightness: temperature and size. So, if you're not very warm, but you are very bright, well, if you're not getting your brightness from your temperature, you must be getting it from your size. Think about that logic. Let's turn it around and give it an analogy that might make sense to people. Let's imagine that a student has a 90 average, but their quizzes are only 80, 81, 82. How would they get a 90 average if they're only getting 80s on their quizzes? Well, they must be doing a great job on their labs. That must be where the points are coming from. Now, if a star is very bright, but it's not hot, well, to what does it owe its brightness? If not temperature, it must be due to a huge size. Now, the best example of this would probably be Betelgeuse. Now, if you look at Betelgeuse, tremendously luminous star, just like Rigel, 150,000 times brighter than our sun. But Betelgeuse only has a temperature of about, let me just try to move this line. It's a bit cumbersome with a mouse. Betelgeuse only has a temperature of, let's say, around 3,300 kelvins. So why in the world would Betelgeuse be so incredibly bright if it's so cool by stellar standards? Well, if it's not getting its brightness from temperature, it must be getting it from size. So now let's compare a couple of other stars and try to figure out which one's bigger. So let's take a look at Betelgeuse and let's take a look at Rigel. Okay, let's look at Betelgeuse and let's look at Rigel. Now here's the thing. What do Betelgeuse and Rigel have in common? Well, Betelgeuse and Rigel are approximately the same in luminosity. They're both around 150,000 times brighter than our sun. So, which star is going to be bigger? Well, Rigel's extremely hot. Betelgeuse is rather cool. How in the world can Betelgeuse be just as bright as Rigel if it's only a third the temperature? What advantage would Betelgeuse have that would give it a similar luminosity? It's so much cooler. Where is it making that up? It's making it up in size. Betelgeuse must be probably 3 times larger than Rigel in order for it to be as bright as Rigel, because it's cooler. All right, let's take a look at, for example, how about Sirius? Let's compare Sirius to our sun, our own star. Now here's Sirius. And here is the sun right over here. So, bear with me. A little cumbersome with the mouse here. So there's Sirius. Well, Sirius is about maybe 12 or 13, or actually more like 20, 25 times brighter than our sun. And it is a little bit hotter. So I guess Sirius's extra luminosity could be due to its temperature. It might not be a whole lot bigger than our sun, but actually it turns out it is bigger. So we really couldn't learn a whole lot from that one. So how about we try a different one? Let's compare, how about Sirius to Polaris? There's Polaris. Polaris is much, much brighter than Sirius is. See the difference? And yet Polaris is cooler. So now think for a minute. Which is going to be the larger star? Sirius or Polaris? Well, the answer is it has to be Polaris by a lot. Simply put, Polaris, how can it be cooler than Sirius and still be, 800 times brighter? It must be much bigger. It has to be making it up. So these are how we can infer size. Now, think about it this way. Look at the luminosity of, let's say, 40 Eridani b, a white dwarf. 40 Eridani b has a luminosity almost 100 times smaller than that of the sun. Almost 1/100th the luminosity of the sun. So, but it's so much hotter than the sun. Look at that. It's literally like almost 3 times hotter than the sun. But yet, it's like 1/100th the sun's luminosity. How can it be 3 times hotter than the sun and yet be only a fraction of the sun's luminosity? Think about that for a minute. Well, the answer is the 40 Eridani b must be much, much, much smaller than the sun. Much smaller. Maybe 1,000th the size of the sun. But it's much, much, maybe 1/500th. But it's much, much smaller than the sun. I mean, how else can it be so much hotter and yet so much dimmer? All right, it must be very, very small. So now, these are the techniques that we use on the HR diagram for inferring size. Now, sometimes you can't really infer size. We had a little difficulty between the sun and Sirius. But if we compare, for example, Barnard star to Betelgeuse, well, Betelgeuse and Barnard star are very similar in temperature, aren't they? Let's take a look. Betelgeuse and Barnard star. See that? They have very, very similar temperatures, around 3,300 degrees. And yet, Betelgeuse looks like it's, literally well over 1 million times brighter than Barnard star. Maybe 10 million times brighter than Barnard star. So what does that tell you about the size of Barnard star? All right, it must be a lot smaller than Betelgeuse. All right, so it's probably 10 or maybe 10 or 100 million times smaller than Betelgeuse. All right, now, by the way, these stars here, Barnard star and Proxima Centauri, they were referred to as red dwarfs. Okay, those are stars that are fusing, but they're not fusing a lot. They don't have an awful lot to fuse, so they're not particularly hot. But remember what we learned about how long a star lasts. The brighter stars, the stars that have larger cores and are fusing helium more furiously and creating that bluer color, they're not going to last as long. But these stars that are very, very weak, that are fusing at a low rate and using up their hydrogen at a very low rate, they last incredibly long. These red dwarfs, they literally might be almost as old as the universe itself. Okay, now one more thing before we wrap it up. It's helpful to kind of add some color to your reference table sometimes. You can see these are your red stars. These are your orange stars. These are your yellow stars. These are your blue-white. These are your blue, and these are your white. You can infer the temperature of a star by looking at its color. You know the red ones are cooler. The white and blue ones are the hotter ones. And the yellow ones are kind of middle of the road. Okay, I hope this has made understanding the HR diagram a little easier for everyone. We'll have plenty of problems to practice. If you get confused, practice some problems, feel free to return to this video again. Thanks a lot. I'll see you next time.